Hi everyone, Dr. J here, and this is going to be the second part of our loading and performance lecture for both fixed wing and copters. Now, just a reminder, you can look at the Pilot's Handbook of Aeronautical Knowledge to get a different overview of the same material that I'll talk about, and also the Remote Pilot Small Unmanned Aircraft Study Guide. So in today's lecture, we'll be talking about thrust and drag. Now, thrust is the power to move the aircraft forward. And on a fixed-wing aircraft, this is created by propellers. Now, the propeller itself is an airfoil, so we've talked about the wings of an aircraft being an airfoil. The propeller is also an airfoil. It, in a sense, creates horizontal lift. It provides a lift-type force, which is acting in the horizontal direction, and it moves the aircraft forward. And it acts in the direction that the aircraft is pointing. So for a fixed-wing aircraft, it's typically the propeller is going to be pulling the aircraft along or pushing the aircraft along in the same direction that the aircraft is facing. On a quadcopter or an octocopter, this is going to be a little bit different. Thrust and lift are both generated by the same set of propellers. And so in order to generate thrust, you have to tip your quadcopter. So if you've seen a quadcopter or an octocopter fly before, you know that when they're moving around, they are tipping back and forth. And this tipping produces essentially a vector decomposition of the total force generated by these propellers. And of course, the propellers are fixed. They're not rotating with respect to the aircraft. And so when the aircraft rotates, the propellers all rotate. And that rotation generates a component of the force that those propellers are producing that goes into the vertical motion, keeping the aircraft up in the air. And then a component goes into horizontal motion. And so that provides the thrust on your copter drones. And as I said, on a fixed wing, thrust is provided by the propeller and lift by the wings, so two separate things. And here's the important thing. Lift acts perpendicularly to the relative wind. So if the aircraft is going up, as in this example, the aircraft motion is up and to the left, the lift generated will be perpendicular to that relative wind, which is coming against the aircraft. And that that lift, in this case, is going to have different components. Different components are going to act against different forces. There's going to be one component of the lift which is counteracting the weight of the plane, and in this case there's actually going to be a component of the lift which is acting against the thrust. Here's another diagram here which just shows this same idea. You have the flight path and the relative wind there, so the plane is going again up and to the left. You have thrust pulling the plane straight ahead of its current where it's pointing, and then you have drag acting on the plane resisting that thrust. And you see the lift there generated by the wings, and you see that there's a component of the weight which is opposed to the lift, and then there's a rearward component of the weight which is broken up differently in this case, where there's a component of the lift which counteracts the weight, and then another component which is counteracting that thrust. It's the same idea here, just broken up in a different way. So that weight now, that rearward component of the weight, is essentially acting as like a drag and being opposed by the thrust. So all these different forces are counteracting each other. And of course, as we said last time, for straight and level flight, lift and weight are both balanced. And now if you have thrust and drag being equal to each other, you'll have the aircraft moving at the same speed. So there won't be any speeding up or slowing down. Now I want to mention one thing here, which is might be a little bit confusing. You can have the aircraft moving up as we had in the last diagram, but you can also have a high angle of attack. So in this diagram, the aircraft is actually moving straight ahead. So the aircraft motion here is straight to the left. The relative wind is straight to the right. And what we have here is a high angle of attack. Now you might be saying, well, what in the world, when would this ever happen? And actually, it could happen in a number of cases. One example is, let's say that you're in an airplane and it's coming in for a landing on a regular airplane now, I'm talking about. Usually the aircraft will be pointed towards the ground, it will be pointed down as it's coming down towards the earth. And then as you get close to landing, the aircraft actually pulls up and the nose goes a little bit higher. And as it comes close to a landing, the aircraft looks somewhat like this diagram. And so that's a case where you have a high angle of attack. You're moving down towards the ground, but your aircraft is tipped up in the air. And so this high angle of attack results in some additional drag that we'll talk about in more detail in a moment. It's actually called induced drag. But you can see here now this lift is counteracting the weight. There's a vertical component counteracting the weight, but then there's a rearward component of the lift which is in the direction of the aircraft motion, and that is dragging on the plane, causing an induced drag on the plane. We're going to talk about that more in a few minutes. But just to keep in mind, an aircraft can be, let's say, tipped up and moving up, or you can have this angle of attack and it's actually moving straight ahead, relative to, in this case, relative to horizontal. So we've talked about thrust. Let's talk about drag a little bit. Drag is going to act in the direction of the relative wind. So thrust is acting in the direction of aircraft motion. Drag is acting in the direction of the relative wind, in the opposite direction, of course, holding the aircraft back. And here is, again, our diagram that we saw before. Because of this drag acting on the aircraft, you have what's called a resultant force on the airfoil. So you have, again, here's our chord line through the airfoil or the wing of the aircraft. You have your angle of attack there, the relative wind. Here's your center of pressure, the place where lift is being applied, the effective location or the center of pressure or center of lift. And there's some horizontal lift. Remember, lift always acts perpendicular to the relative wind. But then there's this drag, and this drag is acting to resist the motion of the plane. And so there's a resultant force on this wing, which is the combination of drag and lift. There's a couple of different types of drag. One is called Parasite Drag and one is called Induced Drag. Kind of funny names, but basically the Parasite Drag is something which goes along with the plane, and then the Induced Drag is something which is happening as a result of forward motion. So let's talk more about what these things mean. Parasite Drag increases with speed. Faster speed means more drag. And there's several different types of Parasite Drag. They're all going to contribute to Parasite Drag, but they're coming from different sources. One is just the shape related to the shape of the aircraft, and this is this form drag. You can see these different profiles of these different airplanes. As these airplanes are moving through the air, obviously they're going to produce more or less drag. You can imagine similarly a car, a very sleek, streamlined, fancy car is going to be able to cut through the air a lot easier than a large truck or van would be able to do, for example. So just moving through the air easier. There's also this thing called interference drag, which is related to essentially mechanical junctions on the aircraft. And so places where different parts of the aircraft come together, the wings with the body, the supports and so on, those areas cause some additional interference such that if you just took the individual components of the aircraft and put them in a wind tunnel and measured their drag, and then you put the aircraft all together and measured the drag, the total drag would be a bit more. And it's because of these junctions where, again, airflow around the aircraft is a little bit more complicated than what we're talking about here, and that turbulent component of airflow causes some additional drag. And then finally you have skin friction, which is related to the roughness of the aircraft. So this might be from rivets on the wing, ridges and little dents and ridges on the aircraft body, just little bits of the aircraft that aren't smooth and streamlined, and that cause some additional skin friction between the aircraft and the air, and doesn't allow the air to flow by easily. Now, induced drag, so we were just talking about parasite drag. Induced drag is going to decrease with increasing speed, and it's also known as lift-induced drag, and this is actually related to what I was talking about a moment ago. This is caused when you have these angle of attack, and that's not horizontal, relative to your direction of motion, and it acts when the downwash off the airfoil points lower. In other words, gets closer, has a higher angle with respect to the aircraft. And that results in lift that points more backwards. So the simple way of thinking about this is just the aircraft is tipped, just like we've had before, and it's moving straight ahead. And so you have more drag, induced drag, which is coming from the component of lift that is acting opposite the aircraft motion. So aircraft motion is straight left, and this component of lift is acting to oppose that aircraft motion. And I haven't said yet, but I should say here, higher angle of attack typically goes along with a slower airspeed, right? So if you're trying to move ahead, straight ahead, the plane is moving and it's got this high angle of attack, you can see that there's going to be more resistance, more air resistance to that than if the plane was straight and level and moving forward. And so that results in a slower airspeed. And so what happens is you have a diagram which looks kind of like this. You have, as airspeed increases, parasite drag increases, and that's due to just the build of the aircraft, how it looks, how its form is shaped. But then induced drag decreases. And at some point you have kind of the minimum possible total drag, the minimum drag there, and there's going to be some airspeed for each aircraft with its particular load, which allows you to minimize that drag. So let's just summarize what we've said so far. Thrust provides the power to move the aircraft forward. Drag acts in the direction of the relative wind and opposes the force of thrust. A high angle of attack leads to more lift. I think I mentioned that in one of the other videos. A high angle of attack does give you more lift, but it also gives you more drag. Parasite drag increases with speed, and it is composed of 3 different types: form drag, interference drag, and skin friction. These are related to the shape of the aircraft, how it's put together, and the roughness of the aircraft itself. So all things that are just related to the aircraft. And then induced drag decreases with aircraft speed and is related to that angle of attack.